Welcome. Let's understand principle to determine maximum ground fault current. Let's see principle to determine maximum ground fault current. The maximum fault current from grounding grid to earth refers to the maximum fault current flowing into the earth through the grounding grid under the fault conditions within the substation, or flowing into the grounding grid from the earth when the fault occurs outside the substation, which is an important parameter that must be fully examined in the grounding grid design. In IEEE 80, the maximum fault current from grounding grid to earth is called the maximum grounding grid current. How to determine the maximum grounding grid current is given in IEEE 80 and detailed. Most of the time, in the substation's grounding device design, the maximum grounding grid current generates the most serious touch voltage and step voltage, which is the most dangerous situation. During ground faults, the earth is used as the return path of the fault current to the neutral of the system. Only part of the total fault current flows from the grounding grid into the earth. The fault, which appears in the substation, may not generate the most serious case, with the largest part of the fault current flowing into the earth from the grounding grid, because a transformer with neutral grounded has a direct conductive path for the fault current returning to the neutral of the system rather than into the earth when the substation has a circuit reference ground. The fault generating the maximum grounding grid current may be a transmission line ground fault at a certain distance from the substation. But the fact is that no simple rule can be used to determine which fault and location will lead to the maximum grounding grid current flowing into the earth from the grounding grid, or flowing into the grounding grid from the earth. A typical shunt situation, when the high voltage side of a substation appears as a ground fault, is given in IEEE 80. Let's understand location of the maximum ground fault current. For a given power system, the most serious fault generally refers to the case with the maximum grounding grid current. Because the current is proportional to the zero sequence, or grounding fault current, or the fault current division factor, and because the current division has almost nothing to do with the fault type, the most serious fault type can be defined as the fault which results in the largest zero sequence current, or ground fault current, flowing into the earth from the grounding grid. For a given location, if the positive, negative, and zero sequence impedance of the fault point is Z1, Z2 and Z0, then if they meet Z1 Z0 greater than Z2 square, then the single line to ground fault is the most serious fault type. If they meet Z1 Z0 less than Z2 square, then the line to ground fault is the most serious fault type. Under normal conditions, in the assumption that Z1 equals Z2, the conditions under which the former single line to ground and line to ground are the most serious fault types change to Z1 less than Z0 and Z1 greater than Z0. When determining the maximum grounding grid current, a number of issues should be considered as follows. The location where the most serious fault occurs may appear either in the high voltage side or in the low voltage side. But in both cases, it may occur either within the local substation or on a transmission line outside the local substation. If the fault relates to a metal structure which has an electrical connection with the grounding grid, the connection resistance can be ignored, and then the fault can be classified as a fault within the local substation. There are no fixed principles to determine the location of the most serious fault. The following discussion can provide a reference, but it should be noted that these discussions do not represent all the location scenarios of the faults producing the maximum grounding grid current. Let's see issue 1. For a distribution substation and whose transformers are grounded on the distribution side, Ig generally appears in high voltage side of the transformer. However, if the ground fault current source of the high voltage side is weak, or when parallel operation of transformers leads the ground fault current source of the low voltage side to be high, the maximum grounding grid current appears as a certain ground fault, somewhere on the distribution circuit. Let's see issue 2. For a ground fault appearing on the low voltage side of the secondary side of the transformer with neutral grounded, the transformer will only allow the fault current to flow through the conductors of the grounding grid, without leakage current flowing into the soil. Therefore, the fault current has no contribution to the ground potential rise. Let's see issue 3. If the ground fault takes place at a remote location of a distribution feeder outside the local substation, the majority of the fault current will return to the fault source through the substation grounding grid and the neutral of transformer, thus there will be a substation ground potential rise. Let's see issue 4. In a transmission substation with 3-winding transformer, or automatic adjusted transformer, the case becomes more complicated. IG may be caused by the transformer's fault in either the high or low voltage side, and hence the two cases should be checked. For each case, it can be assumed that the fault is in the terminal of the transformer, within the substation. In contrast, if the transformer has a dominant contribution to the grounding grid current, then the location of the most serious fault may be on the transmission line outside the substation. From the above analysis we know that, for a particular system, we should take into account several fault locations, leading to the maximum grounding grid current. For each possible location, we should calculate its corresponding value of the zero sequence current. The fault duration depends on the type of the protection procedures used, the fault location and the clearing time of the primary or backup protection. This not only affects the decrement factor dF, but also affects the human body's permitted voltage. If a particular fault has a relatively long clearing time, the corresponding tolerant voltage will reduce. Even if the grounding grid current is not the largest, the situation can still lead the fault to be a very serious one. This situation generally appears in the delta star grounded transformer, which is fed from the relatively weak side of the fault source, and the fault appears at a certain distance from the rural distribution feeders. In this case the fault current on the high voltage side, delta side, may be relatively lower, while the fault on the low voltage side, star side, mainly depends on the faults of the transformer and feeder. If we consider the backup protection time, for example a fault appears on a feeder within a few kilometers of the substation, the backup protection of the fault for the circuit breaker needs a few seconds to remove the fault. Under these circumstances, the permitted voltage will evidently be lower than the corresponding permitted voltage, when the ground fault is on the high voltage side of the transformer. So the most serious fault type and location must take into account not only grid fault current, but also the permitted voltage based on the fault clearing time. Stay tuned to know more about maximum fault current to the earth, fault current division factor, simplified calculation, typical values, influence of seasonal freezing. Thank you for your attention and time. More stuff coming soon. Don't forget to subscribe.